Yes. Yes.
So yeah, so last time when we derived the equations that govern the height and the angle of the final ray which exits the optical system with the initial height and angle, so these were the equations, right? And I said there was a typo, but there wasn't. I think I made a mistake when I went over the equations myself. So this R will be there. So I corrected it everywhere else in the slides that I used to derive the math. So everything up till here where we derived the individual sets of equations for the free space propagation, the refraction at spherical surface, and the free space propagation for the second name, they are all correct. Then when you put them all together, and when I was doing that, somehow I lost this R, so it should be there, and I fixed it. So these are the same, these are the set of equations which match with what is given in slide 23 of the.
So the lecture slide that was posted yesterday, it has the correct R, right?
Yes.
Okay,
so
thanks.
It did from the beginning. I thought it shouldn't be there. That's why I made that comment in the when I was working out the math, but it should be there. So everything is correct.
Okay, thanks.
And I updated it in my math slides, which you can use to work out the math again by yourselves. So all this should be on the website. Okay, so we went over a couple of these examples. I think I'll do more examples in upcoming classes, but just let's go through the math for now. And like last time, just shout out your questions. I was able to see the chat, then the window disappeared, so I'll try to bring it back some other time. Okay, so today we are going to look at something called the matrix formulations. But before that, let me see. So this is done. Yeah, so this is today's class. This is a recap of what we discussed last time. A ray from the left propagates towards the right at an angle with the optical axis, and it suffers refraction at a spherical surface where its angle changes, and then it propagates for some certain distance inside the second medium. So medium 1 is on the left hand side of this vertical line, medium 2 is on the right hand side, and finally the beam, the ray of light can be drawn as like this with an angle alpha 2 and a height x2 with respect to the optical axis, and the set of equations that relate x2 and alpha 2 with x naught, alpha naught, which were the input parameters, are given over here. So three sets of equations for three phenomena, two of which are very similar. Free space propagation in medium 1 and 2 basically have a difference in the variables in the equation, but their form is the same. And the other set is the refraction at spherical surface, which is the interface between medium 1 and medium 2. So I generalized the forms of the free space propagation equation. You can see x1 equals x naught plus alpha naught and so on. And for the second one, it's x2 equals x1 prime and so on. So it's basically x out, the output side, equals x in plus alpha in times d, which is the distance the ray traveled basically. What it does is it changes the height. When the ray is traveling at an angle, it changes the height of the ray with respect to the optical axis, but it does not change the angle. So the output and the input angles, alphas, remain the same. Obviously, if the ray was traveling parallel to the optical axis, where the alpha out equals alpha in equals 0, there wouldn't be any change in the height either, because alpha in would be 0, and it would just keep traveling parallel to the optical axis. So this is the general form of the free space propagation equation. And this is the general form of the refraction at spherical surface equation, which takes into account the refractive indices of the input and the output media, n in and n out, amongst other things such as the angles and the radius of curvature of the spherical surface. So we will remember these set of equations for this class, and we will be using them later on as well. Okay, and when you put them together, these are the final forms like we just discussed. All right, so now here's the thing, like we did go through a fair bit of complicated geometry and so on to analyze just a simple case where a ray was just suffering refraction at a spherical surface after some propagation and then propagating a little bit more. So imagine if you have a more complicated optical system where there's one lens with two surfaces which are curved, and maybe more than one lens, multiple lenses, like suppose inside a DSLR camera or your iPhone, then you wouldn't want to do that much geometry to solve the problem. That would take forever, and it's also difficult to program it into computer softwares. So there's a better way of doing the math, and that's what we're going to discuss today. But the reason for learning the geometry was to figure out how exactly the rays bend and so on, and how the relationships are derived. But this is a very general form of an optical system. So imagine in this yellow box, there's some very complicated optical system with multiple lenses or stuff like that. Yeah. So and there's a ray which enters the system with height x in and angle alpha in with respect to the optical axis, and a ray which exits the system, alpha out, x out. And the medium on the left hand side is with refractive index n in, and that on the output side on the right is with n out. So this is all, everything is kept very general. And if suppose in the case everything is air outside the optical system, then n in would equal n out equal 1. But we are keeping everything general for the time being. Okay, so what is the matrix representation of the ray? So this is something that's going to make our math a lot simpler. And the concept is that with respect to a reference plane or line, such as the optical axis, a ray of light can be very simply defined using two coordinates. Its position with respect to the optical axis, which is given by the height, and its slope, which is given by the angle. And we also take into account the refractive index in which the ray is traveling. Obviously, in the case of air, this would be 1. And we have this matrix representation, which takes into account the height, x, and n alpha, the slope of the ray. So this matrix, this simple matrix with two elements, is sufficient for us to define the properties of the ray in an optical system with respect to the optical axis, which will always be there. Now, what we can do is we can write a matrix for the output side. So n out, alpha out, just like in this slide, I wrote n alpha. So this is n out, alpha out for the output ray. And its height with respect to the optical axis is suppose x out. So x out equals some matrix times the input side matrix. So n in, alpha in, and x in. The matrix in the middle with the terms m is called the system matrix, and this defines all the properties of this complicated optical system. So now we have one simple equation which relates the output side or the properties of the output matrix of the output ray with that of the input and with respect to a system matrix. Okay, so this is what is given over here in your lecture slide. So n out, alpha out, x out equals the system matrix times whatever is there in the input side. Now all we have to do is determine what these elements of the matrix M11, 12, 21, 22 are, and we'll see that these all have general forms, and these are very easy then to program into computer systems and so on, and makes our life a lot easier in solving complicated optical systems rather than having to resort to all the geometry that we worked out in the previous lecture. So one thing we have to remember is we have to finally still solve this equation and equate these terms. So you'll have to remember your matrix multiplication, which is given over here, for two very general matrices with 4 elements. The matrix multiplication is carried out in this form. And I suggest you revise this a little bit. You would never be asked in this class at least to do more than like four term matrix multiplications, but just make sure you remember which term is multiplied by which term and then what the additions are to get the final terms in the final matrix. So this is the general matrix multiplication, and I've done that here for multiplying the system matrix with the input matrix. So M11 gets multiplied by N in alpha in, plus your M12 gets multiplied by X in, so that's the first term, and so on. So you have two terms in the final multiplied version. And then we can solve this by equating the terms. So N out alpha out, the first term in the left-hand side matrix gets equated with the first term in the right-hand side matrix. So this is N out alpha out, and the last term or the second term in the left-hand side matrix equates with the second term in the right-hand side matrix. So that's this one. Okay. So now let's take a look at one example of, actually not one example. So we have these two cases, right, that we previously discussed, the free space propagation and refraction at spherical surface. So we will now see how the matrix multiplication, the matrix formulation can be applied to these cases. So we'll first take the case of the free space propagation matrix, otherwise called translation through uniform medium in the lecture slides. So translation through uniform medium case. So I have drawn out again the case for the free space propagation. You have one ray which is just traveling in space. So in this system, although I have generally pointed out N in and N out, there is no difference, right? There are no two media to consider. There's just one medium, which is whatever this space is. So N in equals N out. The input height for the ray was X in. The angle or the slope was alpha in. And after propagating a certain distance d01, this is the final version of the ray. So we can again remember from previous lecture, the angles have not changed. So alpha in equals alpha out. You can see that visually, but I've kept them in a general form. But the height has changed. So X out and X in are not equal to each other, but they're related. So I have from my previous slides the equations which equate the, so for this system, suppose I could have written this kind of a matrix, right? N out, alpha out, X out equals system matrix. The system matrix which governs this system times the input matrix. Multiplied it out, solved it, and got my final forms of the two equations, which I have put over here. So here, right? Now what we will do is, why we are doing this exercise is because we want to figure out what the values of these coefficients are. What is M11, what is M12, 21, 22, and so on. So in this case, remember, alpha out equals alpha in. So I've put that here. X out equals X in plus this height, which we determined in the last class, is equal to alpha in times d01. You can go back a few slides and see over here the general forms, X in plus alpha in times d, and alpha out equals alpha in. So this equation, free space propagation equations, general form is what has been put down over here. So now it's just simple algebra. So and also in this case, so N in equals N out. So I've just put this over here on this side. So I can manipulate this equation a little bit. So the first equation that I have, I can manipulate it by putting in an extra X in multiplied by 0. So look at this equation. So your alpha in is basically N in times alpha in times 1 plus 0 times X in equals this first equation, right? So I've put that over here. And the second equation has also been manipulated and put down over here, this one. So I'm basically equating the X out with this X out, and the alpha out with this alpha out, right? So if I equate the coefficients of the equations, I get M11 equals 1, M12 equals 0, because I can see that in this equation there is no X in term, right? Alpha out equals alpha in. There's no dependence on the height. So X in, anything, it has to go to 0. So anything, 0 has to be multiplied with X in, right? So basically M12 has to become 0. So M12 equals 0. And then M21, this one, this term. So I have to equate this term with this here. So alpha in, alpha in. So M12 basically becomes D01 over N in, right? So M12 is D01 over N in, to make this term same with this term. So it's D01 over N in. And M22, again, I have an X in term. I have an X in multiplied by M22. So M22 is 1. So we just used the equations that we derived from the previous class, wrote out the matrix formulated equations for this case, and we equated each term in the equations to figure out what the coefficients were. And now we can bring them all together and write our free space propagation matrix, which was M11, M12, M21, M22 as M11 equals 1, 12 equals 0, 21 is D01 over N, 22 is 1. So this is the form of the general free space propagation matrix, and this is always going to be true. The only thing you can change is the distance the ray propagates and refractive index, and you can see there is no other term, because we can see physically that all that can change in this system, or all that can affect the ray, are the refractive index of the medium in which the ray is traveling and the distance that it has traveled. And so that's exactly what's in the matrix. And this will always this will always be true. So you can always use this in any general case, and you wouldn't have to worry about working out all the bulk of the geometry or trigonometry from last class. And this is what is given over here, translation through uniform medium. So this is your free space propagation matrix. And you see this is the input side, output side. And the system matrix is 1, 0, D01 over N, and 1. So 1, 0, D over N, and 1. This is just general form. I've written general form. This is how it's derived. So this, I basically worked out this part of slide 28. This is how the derivation of the free space propagation matrix is done. So before I go into the next case, if you have any questions, I'll give it a moment. So just to quickly recap, I drew my system, wrote out the matrices, and then I brought the equations that we derived from previous class, equated the terms, the coefficients, and derived what the 4 terms of the matrix is, and deduced this is the free space propagation matrix. Okay, so let me go forward then. So the second case is the refraction at spherical surface. So again, these are the only 2 phenomena that we have to worry about, right? The second one, the refraction at spherical surface. So any optical system, only, even though it would have a number of lenses or mirrors or whatever, there's only 2 phenomena that can take place in the case of lens-based optical systems. One is propagation and one is refraction. So there are just 2 matrices that we have to determine. One we already did, the second one we are going to work out now, and we will see that these 2 would be very important tools that are going to help us solve complicated systems later on. So the refraction at spherical surface matrix. So I've drawn out the case over here, similar to what we discussed last time. So the ray enters the optical system here, or whatever is the medium through which it's getting refracted, and its angle changes. So remember this propagation, there's no propagation here. I've just drawn this ray out so that we can point out the angles and everything. But basically, we are just concerned with the ray entering here, and just when its angle has changed. Then all the propagation before the refraction, that is in the left-hand side medium, and the propagation in the right-hand side medium, will be taken care of by the free space propagation matrix that we just discussed. So we are just considering the fact of refraction at this interface, and we're going to concentrate on this point for this discussion. So remember, the height does not change. X in equals X out, no propagation. Only refraction at interface is what we're going to focus on. So alpha in and alpha out are not equal. Alpha out is related to alpha in by some certain way. And the two refractive indices on two sides are different in this case. So N in and N out. So imagine the ray going from air to water, or glass to air, from one medium to another, basically. Okay. So I can write my equations from the matrix formulations again. To begin with, I would write out this form. So N out, alpha out, X out, the output matrix equals a system matrix for this system times the input matrix. And then I'm going to figure out what these four terms are going to be. So I've written out those and then done the multiplication and written out the final forms of the equations here and here. Okay. Then just so that I can have these equations written out in a form which would make it easier for me to compare with the refraction equations that we derived in the previous class, which are given over here, I've done some algebraic manipulation of the equations. So here you can see refraction at spherical surface is X out equals X in, and alpha out equals some terms. So I've done some manipulation of the terms, and I've written them out in the form of X out and alpha out, right? So X out equals 2M21 times N in alpha in plus M22 times X in. And alpha out is basically, I've divided the right hand side by the N out. So N in over N out, and here X in over N out. Okay, so this is the equations. I've just cleared out this side, and this is the final forms of the equations that we're going to focus on. So in this case, X out equals X in, and alpha out equals this right hand side term. I've copied them from the first slide, from the recap slide. And now, just like for the case of the free space propagation matrix, we are going to equate the coefficients, equate the terms. So X out equals X in, right? So there's no angle dependence in this equation, you can see. So anything multiplied by alpha in, so this term has to vanish, and this has to remain 1, and so on. So we'll take the terms one by one. So equating the coefficients, I've written them out in a way so that it makes it easier for me to compare, so that I can compare alpha out with this alpha out. So basically this side, N in over N out and so on is written over here, equals this term. So here, then I have to compare X out and this X out. So I've written out X in like this. X in equals 1 times X in plus some 0 multiplied by alpha in, so that I can compare easily. And then I've written out this term over here as well. Okay. And now I equate the coefficients. So I see with this first term, whatever is multiplied in front of alpha in, N in, N out, N in over N out is there. So M11 we can easily see is equal to 1. The next term, so M12, this will require a little bit of working it out. So M12, this is how it's worked out. M12 x multiplied by x in over n out equals this term, n in minus n out over n out times x in over r. Right? So these terms are equal. And from there we do some manipulations. So basically your x ins go away, and this is the final term that you're left with, n in minus n out over r. And just to make it look such that we have the output on the left hand side, so we have taken the negative sign out, so it's n out minus n in over r with a negative sign in front. So this is M12 here. So I've cleared out that part. So this is M12. And you can revisit this in your own time. Just go over the math here and just practice it by yourself. It's not very complicated math at all. Then we come to the M21 term, right? So in the M21 term, we have to equate this term with this term. Very easily, we can see that M21 has to be 0 for this term to vanish, because there is no angle dependence term in the first equation. So M21 becomes 0 and M22 becomes 1, because x in equals x out and x in on this side, right? And putting them together, this is the refraction at spherical surface matrix. So M11 is 1, M12 is this term minus n out minus n in over r, M21 is 0, M22 is 1. Okay, so this is the term which is given over here. So let's compare 1, 0, and 1. So 1, 0, and 1. And this large term is your output side minus input side over r with a negative sign. So output side n prime minus your input side over r with a negative sign in front. So this is the refraction by spherical surface. So now we have deduced these two important matrices. One is for the free space propagation, and one is for the refraction at spherical interface. So now these are the two matrices that we can use, and we wouldn't have to worry about all the geometry and stuff and solve complex optical systems. And I will show that now. But if you have any questions, I can pause for a little while. I think the math here was pretty straightforward. Just remember, don't make mistakes when you're working out the matrix multiplications. Sometimes they can be a bit tricky. You have to remember which term to multiply with which one, and so on. And so this slide, slide 28, is also pretty important for you to solve your problems, also for the midterm, because you would have to refer to what the forms of these matrices are when solving complex optical systems. Well, they won't be too complicated, but whatever. So let's take a look at one of the examples. The exactly same example that we solved last time, right? And it took us a really long time to figure out what the solution to that problem was. We had to draw a bunch of angles and use an arc length relationship, alternate angles, opposite angles, all that stuff took us like 40 minutes to solve that. So in this case, we are going to actually solve the same problem, but using the matrix formulations, and see how it will make our life a lot easier. So slide number 29 in the lecture slides, example of spherical surface, same example here in slide 20 with all these big equations and so on, and all the math that I worked out. But this time with matrix formulations. So again, just quickly, definition of what the problem is. Two media in, so I've actually changed my notations to n and n prime as well from this slide, from this problem, to align with the notations used in slide 29, right? So all the notations here match with my notations here. So medium on the left has refractive index n, medium on the right has refractive index n prime. The input ray has an angle alpha naught and a height x naught with the optical axis. And the very final ray, which is out of the system, has the slope as alpha 2 and height x2 with the optical axis. But before the ray goes from this point to this point, it goes through free space propagation or translation through uniform medium 1. Then it comes up to here. Its height changes to x1. It suffers refraction at the spherical surface, which doesn't change its height, but changes its angle. So alpha 1, so dotted line is what the ray would have traveled if this interface or the second medium was not there. And the solid line is what happens to the ray. So the angle becomes smaller. It bends toward the normal. Assume, of course, n2 is n prime is greater than n. For this case, if it was the opposite, it would bend the other way, right? So in this case, suppose it's going from air to glass or air to water and so on, from a rarer to a denser medium, basically. So angle changes, height remains the same. So x1 equals x1 prime, and then it propagates for some distance more inside the medium 2, and that does not change its angle. So alpha 2 equals alpha 1 prime, but changes its height. Right? Same as the previous case when we solve this. I've drawn up the radius and pointed out the center of the spherical surface. So again, these are paraxial approximation, rays traveling at angles very small with respect to the optical axis, and we have zoomed in to one point of the large sphere, large spherical surface. So it's been approximated in the form of a straight line. This is considering this is a large spherical surface from last time. So this time we are not going to do any geometry, just not worry about what the ray is doing and just use the matrix formulations and see if it works. And remember, for the matrix formulations, when you have to use that, always remember, this is the very important thing. You have to write the matrices from the output side to the input side. If you forget this order, which happens a lot, and I have also done this a lot, you wouldn't get the final answer, which is correct, because the terms would get, the orders would be reversed. So your multiplications would give you different results than what would be the correct version. So remember, from output side to input side, which means that we have to go from right-hand side to left-hand side if the ray is traveling from left to right. Okay, so I'll explain what that means. So first I write the output matrix. So output, so remember, n out alpha out, in this case n out is n prime, right? N prime times alpha out is alpha 2, so alpha 2, and the height is x2, so x2 equals some large system matrix, m1, m2, whatever, times the input, so n naught alpha naught, sorry, n and alpha naught and x naught. Now the matrix inside this optical system would be a combination, or basically a multiplication, mathematically speaking, a multiplication of 3 smaller matrices written for 3 individual phenomena that's taking place. First free space propagation, then refraction, and then free space propagation, right? So if we combine the 3 phenomena, what we would be left with is the system matrix of this optical system. And we have to write out these individual matrices from output side to input side. So first we will, so going from right to left, from output side to input side, we'll first write out the free space propagation matrix for medium 2. So free space propagation in medium 2. That means propagation over distance d12 is the first matrix which is written. Next, we have the refraction at spherical surface, right? Going from right to left. So refraction at spherical surface. Then we have the last one, free space propagation in medium 1. So free space propagation in medium 1. And finally, what's the last thing on the left-hand side? The input. So this is the input matrix, right? So output, going from output to input, right? From output side to input side. So output side is the first term, equals free space propagation in medium 2, refraction in medium, then free space propagation in medium 1, and finally the input. So this is the order. Remember not to forget this order in which the matrices are supposed to be written. Right? Very common thing to do is what many people do is write the output and then just write the matrices like free space in medium 1, then refraction, then medium 2, and then multiply with the so you will not get the correct answer in that case. Okay, so we have our general forms of free space propagation matrix over here as we derived previously, and refraction of spherical surface matrix as we derived in the previous slide over here. And now we'll just replace the terms in these matrices based on each special case. So these are the general terms, remember. So yeah, okay. So what I've done is I've written the output matrix here. Input matrix remains the same here. And then I've changed the terms, plugged in the terms from these general forms, right? So first we have to look at free space propagation in medium 2. So I'll just pick this matrix. So remember again, I said this slide is pretty important for problem solving. So if you just have this slide and nothing else, you can solve all the problems. So just look at the translation for uniform medium matrix, or what has been summarized over here. So in this case, the medium has refractive index n prime and the distance is d12. So I'll basically replace n by n prime and d by d12 and write it out over here. So 1, 0, and 1 remain the same, and d over n becomes d12 over n prime. For the refraction at spherical surface interface, I'll do the same thing. So n out in this case is n prime, right? Out it means the medium in which the ray is going into. And input side, in this case, n in is n, r is r. So I'll just replace those. So 1, 0, and 1 remain the same, 1, 0, and 1, minus, it would be n prime minus n over r, n prime minus n over r. And again, free space propagation in medium 1. So this is same as this one, except for in this case, the distance is d01 and the refractive index is n. So it's d01 and n. And that's it. Just one step. Look at the problem, write out your matrices, look at the matrices from the general form, substitute the terms, and that's it. Now this can be solved very easily in computer programs as well. You will obviously have physical numbers for these. We are doing general forms, like you would have like 5 meters, 10 centimeters, whatever. And you would know the refractive indices like 1, 1.5, and so on. So you can just, and the radius of curvature of the lens as well. So you'll just plug in the numbers and maybe in MATLAB or something, and it will give you the solution to this matrix. For the time being, and because we are learning in this class, we are just going to solve the matrices by hand. I've done this here. You can revisit this and do the math by yourself. It would also help you brush up on your matrix multiplication. So this is what is done. The way I do it is basically I again go from right to left. I multiply these last two matrices first. So 1 times 1 plus this term times this term here, and so on, right? So these two matrices have been multiplied to get this matrix. And then the first matrix is just written over here. And the first matrix is multiplied with this matrix to generate this large matrix. And finally, we multiply this large matrix, which is now, by the way, the system matrix for this optical system. Right? This is the M11, M12, M21, M22 term. With the input side, we multiply these two to get this is the final version, right? And we equate the terms. So n prime alpha 2 would be equated with this first term, and x2 would be equated with this large second term. So first term, n prime alpha 2 equals, so just bring this down over here, plus this term here. Okay. And I've done a little bit of manipulation. So basically, I first divided both sides by n prime. So n prime goes down here, and then just cancel out the n's over here and so on, and n prime. So and I've taken this negative sign inside, so it's n minus n prime over n prime r, and also done some manipulations here, and this is basically the final form, right? So usually I work out this in the whiteboard in class, but the online class seems to be saving me a lot of time, because this would take at least like 5-10 minutes or something, assuming that I don't make any mistakes in the multiplication. But yeah, so this is the first term, simplified. And the second term is basically your x2 equals this large term over here, right? So n prime minus n over n prime, and so you do the same manipulations as like last time, and you get this is the final form. So again, best to just look at these slides and practice this by yourself. Just work it out by yourself. And I basically take this term and summarize it over here, and take this final term, the final form of the x2 term, and summarize it over here. And I've copied the versions from the first slide over here. So compare with what we deduced using geometry. It's exactly the same. Some notations have changed. So in place of n1, I've used n. In place of n2, I've used n prime. But again, this is the r that I missed out last time. So that's here. Everything else is the same. So we basically derived whatever we did last time, but in a rather short period of time. And again, the other take-home point is that it's not easy to solve geometry using softwares and stuff like that that we can do by hand, but you can program matrices inside softwares and computers. And if you're analyzing large, very complicated system of lenses, 4 or 5 lenses and so on, this is the way to do it. Basically, it saves a lot of time, and just one thing you would have to pay a lot of attention to is the matrix multiplication, if you're doing it by hand, obviously. If you have real value numbers and you put them in MATLAB, this is done very fast. So you would have, in a matter of moments, actually. So when doing it by hand, you would have to keep in mind that you don't make any mistakes in the matrix multiplication, and that you remember the order in which you're writing out the matrices, and just refer to these 2 matrices, and you can solve any complicated mathematics, any complicated optical system. Okay, so that basically brings me to the end of this math section. I wouldn't have any more math to work out, at least when going through the rest of this lecture. But I would work out more examples, but I didn't want to put the examples in this slide, in this lecture for today, so that it doesn't become like too much math has been discussed. So this is the end of the math slides from me, but we will have to still go over the rest of the lecture slides.